in my personal interest in studying genetics around high school time. It was a pretty exciting time with pretty rapid changes. It seemed like a really interesting phase of science, so I kind of jumped in and thought it was pretty cool. Today, what I want to talk about is to see if I can move some of that enthusiasm to anybody else who, and so I want to stimulate some thought about some of the new things that are coming up in genetics, particularly bioengineering, and more specifically genetic engineering. I'm going to do this by talking a bit about the history of bioengineering, review CRISPR-Cas9. Sounds pretty exciting so far, doesn't it? And present use of genetic engineering. Then possible problems associated with genetic engineering. Then hopefully we'll have more time to talk about those kinds of concerns or things that you have hope for the future of use of genetic engineering at the end of our discussion. So I'm hoping not to talk too long. Oops. Bioengineering is the use of cells or up to complete organisms for the product to produce foods, tools, or other things of use for humans. The historic history of this is, I think, it's interesting in that the beginning of bioengineering actually goes back to such things as use of yeast for brewing, started about 10,000 years ago. The bacteria for use in making yogurt, cheese, again, about 10,000 years ago. Then the domestication of plants and animals somewhere about 10 to 8,000 years ago. And this gradually just sort of moved along for a long period of time, thousands of years. It was gradually improved over time. So lots of different things happened over that period of time, but there were no big, great gotcha kinds of moments regarding development. Then the next really big things started coming along in the mid-1800s. The understanding of dominance and recessive in genetics. Mainly Gregor Mendel is remembered there as the instigator and first person to really understand it. Also about the same time was Darwin, Lamarck, and Wallace, the understanding of how the genetics moves things along as far as understanding of evolution. So that's several thousand years between those two things that I think are really particularly important for bioengineering. Then the next really big step, now we've gone for thousands of years, and the next really big step is 100 years later in 1953 when Watson and Crick identified the chemistry of DNA, which makes the rest of the things I'm going to talk about possible. Again, and the next really big step, I think, to marker, I guess, in time is the human genetics, the Human Genome Project, which is the identifying of the DNA in humans and identifying of genes in the human genome. And that was published, I think, in 2003. So we're now getting down to 50 years or so. And then development of CRISPR, Cas9 in papers published in 2007. So really fairly recent. And that then what we're looking at is we've gone from thousands of years to hundreds of years to 50 years to almost immediate changes in all of these important kinds of things. Now there's such things as commercial use of the genetic engineering, and the most common people would remember right now would be the mRNA vaccines development. You can buy genetic stuff, genetic changes can be made so that you've got things that you can buy. The thing that's most important, I think, is the change in time. It was done for a long period of time with really slow development. And then now that information is just shooting up. And the difficulty here is what was mentioned in the reading, and that is that it's happening so fast. How do we develop morals and ethics to support the science, the use of science? So a quick description of CRISPR-Cas9 is the CRISPR component. I really like the name, and you'll find the reason it's called CRISPR is because it stands for, and I have to read it, clustered, regularly interspaced, short palindromic repeat sequences of DNA. Everybody's to remember that at the end of the talk, okay? And the Cas9 component is an enzyme which allows genes to be cut, specific genes to be cut out of the DNA, or it actually can be used, I think, for RNA as well. But that information is then transferred to messenger RNA. The messenger RNA, through several different methods, can be moved to another cell. As far as I can tell, there are almost no limits to what can be moved. And I have to ask Amanda about that later, but it seems to be able to, that since almost all life depends on DNA and RNA, that chemistry holds for one kind of life to another kind of life. So that was the reason I like that photosynthesis story. Can we do that? I don't know. The mechanism of the CRISPR, I'll show a picture. I think it may help some. So basically, that DNA up there, then the CRISPR component identifies the genes and says, this is a gene. This represents, this is the chemical makeup of that particular gene. Then the next thing that comes along is the Cas9, which is as I mentioned, it's a protein. And what it does is it's able to slice out that specific gene. And as it's doing that, it's hooking it up to the messenger RNA. And then the slice can come out of anything. So for example, with the COVID vaccines now, they've taken the protein, they've taken DNA that makes the protein for the virus's spike protein. They've taken that out, put that on the messenger RNA, and moved that to, we can now give it to human cells. Messenger RNA goes to the human cell. The human cell's regular cytoplasmic mechanism of making protein makes up the COVID-19 spike protein. The body then recognizes that as an abnormal protein that's not supposed to be there. And because of that, then antibodies develop. It's that antibody that gives us the resistance to the COVID. Is that close, man? A fairly straightforward process, but the details in that are just really hard to get my mind around. All the technology that goes into doing that. It's exciting, but difficult. I'm not taking a test on it either. Okay. Now, the next thing I want to use is a slide about medical uses. The medical uses at this point are pretty straightforward, and for the most part, I don't think cause much concern in their use. So some of the things that are available in medical use today. The colony stimulating factor produces white blood cells. So people whose white blood cells are suppressed from cancer or AIDS or any of those that cause depression of the the available white cells, that can be used to stimulate those from your bone marrow. Erythropoietin for anemia. There's several reasons to use that. People with cancer would use that after chemotherapy. The dialysis uses up extra red cells and become anemic from that sort of thing. Factor VIII is a replacement of the clotting factor that's missing in hemophilia. We used to treat hemophilia by using factor VIII from other animals we collected, but now we can make it. It can be built in one of the probably bacterial factories, essentially, so it can be used now much easier, and it's much cheaper to produce. You don't have to take it from a living body. Growth hormone, again, used primarily for short kids. If they're too short and they fall out of the normal ranges, then they get sent to one of the major centers and get started on growth hormone. Insulin's now made essentially artificially. We used to have to use, when I started practice, we were using insulin from cows and pigs, and don't have to do that anymore. Then this is one I don't know much about at all, but platelet-derived growth factor stimulates wound healing. Tissue plasminogen factor dissolves blood clots after heart attacks or strokes. And then now the vaccines we're talking about with COVID-19, but there are multiple other vaccines that use very similar kind of production. There's a bunch of other ones. And new ones seem to come out pretty regularly. Just some I had absolutely no idea was becoming available, but seems to be reasonably available, those sorts of things. These seem to have, there's not much question that these are probably useful and not and harmful in the same way, for example, that any medicine would be. It's going to have some side effects to it, but nonetheless, really very helpful and more helpful than harmful. The next thing is that what's going to happen in the future, and that was sort of my story with the advertising this morning, and that is that it seems apparent to me that likely we're going to become more facile with using more and more complicated genetic components for things that are highly complicated and to treat. For example, mental illnesses. Maybe we can adjust intelligence, complex and other complex body sorts of systems. In other words, maybe we can get around to treat things like diabetes by treating it from a genetic standpoint to allow each humans who should be producing insulin but aren't, can manufacture their own again. And those probably are not going to be too difficult to sell to the public, literally and figuratively. And but then the next group of things seem to be what I would be concerned about as having to develop morals and ethics that aren't present now, so that we can actually use them in some form that's acceptable. For example, what I mentioned, I'm calling these cosmetic genes or cosmetic use. For example, probably going to be able to change eye color, eye shape. One of the things I talked about, the mRNA going to cytoplasm, and the cytoplasm of the cell, the outside the nucleus is the thing that makes the protein that is useful for us. Protein, basically we are protein. Think about where I was going with that. Basically, the cosmetic uses. The difference with the mRNA and the cytoplasm is that it doesn't go to the next generation. However, now putting these sorts of genetic information into the nucleus, the DNA of the accepting cell, allows it to be moved on from one generation to the next. So many of these things, for example, the choices that are going to come up with this can be determined by a parent and perhaps decide to genetically design their upcoming child. So, for example, eye color, eye shape, body shape, skin color and texture, hair color, enhancement of physical activities, the ability to jump higher, run faster, swim underwater longer, whatever those kinds of things might be possible. And another thing that goes along with this is determining the sex of the child coming up. So as I mentioned, Olivia's past that because her parents couldn't make those kinds of decisions. However, as she gets into an age regarding her own children, she may have some of those choices. She could choose whether she has a boy or a girl first, or both, or let it come up with just the natural selection of the egg and sperm. Other things, even more complicated, such things as personality traits. Do we want a nice kid? So, in my company, I'm going to have a blue-eyed, blonde-haired, extremely intelligent, 6'4", basketball-playing girl. So these things are all becoming possible. Like right now, there's enough information to do such things as deciding the sex of your first child, emphasizing the sex of each child. All that needs to happen is that there's external fertilization, and then the fertilized egg is reimplanted in following a normal pregnancy sorts of things in a usual fashion. But I'm not sure how many genes we could change here and how much we could change a person, but we can. And we can do that now to some degree. So the big questions actually are still coming, and that is, who makes these decisions? The parents decide about the children, the sex of their children, or their hair, et cetera, et cetera. Or do governments make those kinds of rules? Or do social societies, such as religious groups? So who's going to make these? Who's going to make these decisions, and how are we going to make them? Who's going to have input into it, and who's going to enforce the decisions? So basically, the tools, I think, for genetic engineering they're here at the chemical level. We can do that stuff now. It's like atomic energy. Once the genie's out of the lamp, we can't put it back. So it's up to us. We've got to figure out some way of using these things in a moral and ethical fashion. And what that is, we've all got to have input into it. Well, this actually is a mutation of the same kind of dog as this, but it's a single gene mutation. So I was talking about sports stuff. So this guy's a lifter, this guy's a runner. I mean, we can choose that now, the next generation, or maybe choose that. I think it's pretty close because, as I said, it's a single gene. don't be uncomfortable, Olivia. I'm not going to push the weightlifting girl, okay? So, like any tool, these genetic changes, the use of the tools to make these changes are just like any other tool. And that is, the tool's not the problem, it's how we put it to use.